All right, let's jump right into this explainer. Today, we're putting the two heavyweight champions of explainable AI head-to-head to finally illuminate the ultimate black box. We're going to break down exactly how we can figure out what these incredibly complex machine learning models are actually thinking. And we'll do this by looking at the two most popular techniques out there right now, SHAP and Lime. So if you're working with data, or honestly, even if you're just impacted by algorithms in your everyday life, which is basically all of us at this point, understanding this matchup is absolutely crucial.
So picture this. You go to the bank, you apply for a loan, and you're denied. Not by a human, but by a gradient-boosted model running, say, 500 trees. That's incredibly frustrating, right? Well, with the EU AI Act's August 2026 compliance deadline creeping up on us, you are actually legally owed an explanation for that denial. This right to an explanation has completely shifted model interpretability from a cute, nice-to-have feature to a strict, hard and fast legal obligation for high-risk AI. So how on earth does a bank actually figure out why their algorithm said no? Well, we have to somehow peek inside that seemingly impenetrable black box. You see, a model's test accuracy only tells us how often it's right. It tells us literally nothing about why. A super accurate model could secretly be relying on totally bogus, spurious correlations, or it could be completely failing on specific edge cases. And its overall accuracy score, it would completely hide that fact. We need tools that pry open the lid and show us the actual mechanical gears turning inside that decision-making process. Let's ground this with a real-world scenario using our hypothetical applicant-specific data. We're going to track exactly how our two contender models evaluate these specific features. Okay, so our applicant makes $72,000 a year, has a pretty solid credit score of 710, a debt ratio of 0.35, they've been at their job for 4 years, and they're asking for an $18,000 loan. The AI looks at this exact profile and just says, denied. Let's see how our two explainability tools interpret this exact rejection. Introducing our very first contender, Lime. Lime stands for Local Interpretable Model Agnostic Explanations. What it does is elegantly generate these synthetic neighbors around our applicant to see what a simple linear regression would do locally. What does that mean in plain English? Basically, it treats the complex model as a total black box. It takes our applicant, tweaks their data just a little bit, maybe test an income of $45,000 and then maybe $90,000, and it watches how the model's prediction changes. By plotting out all these synthetic neighbors, Lime draws a simple, super understandable line that mimics the complex model's behavior right in that specific neighborhood. And in the other corner, we have SHAP, or Shapley Additive Explanations. This one utilizes actual Nobel Prize-winning game theory from 1953. It treats features like players in a game, collaborating fairly for the final prediction payout. So instead of just drawing a simple line like Lime does, SHAP asks a much more profound question. It asks, if we treat the loan denial as a sort of penalty, exactly how much of the blame is mathematically owed to the credit score versus, say, the debt ratio? It calculates the precise contribution of each and every feature by systematically adding them into the model in every possible order. All right, let's ring the bell for round one, scope. We're looking at local versus global here. Now, this is where the specific differences between these tools really start to define exactly when you should use them. The absolute crucial point to remember is that Lime only generates a local explanation for our single loan applicant. SHAP, on the other hand, can do both local explanations and aggregate those values to explain the entire model globally. Lime is fantastic if you just want to look at one person's specific loan denial. But what if a regulator knocks on your door and asks, hey, how does your model weigh credit scores on average across all of your customers? Well, Lime simply can't reliably tell you that. SHAP, however, can aggregate all of its local, individual explanations into a massive global view. It gives you the micro and the macro perspective, all wrapped up in one single framework. But here's the real catch with Lime's local approach. Running it twice on the exact same applicant can actually yield completely different feature orderings. And that's because of its stochastic sampling process. Because Lime generates random synthetic neighbors to test the model, it's basically fundamentally unstable. I mean, you could run Lime on our applicant right now, and it might tell you their debt ratio is the biggest factor. Run it again 5 minutes later, it might say their income was the biggest factor. In a high-stakes, heavily regulated environment, that kind of instability can seriously diminish operational trust. SHAP, on the flip side, guarantees consistency. This means all of those feature contributions sum up exactly to the prediction, and that is the absolute gold standard required for compliance trails. Because it's rooted in rigorous mathematical axioms, a SHAP explanation is an exact decomposition. If you add up the SHAP values for the income, the credit score, and the debt ratio, it will perfectly equal the model's final probability score, every single time. This makes SHAP's global bee swarm plots and local waterfall plots incredibly defensible when you're sitting across from an auditor for something like the EU AI Act.
Moving right along to round 2, computational speed.
Listen, consistency is great, but it really doesn't matter much if you have to wait a lifetime for it. If a bank needs to process 10,000 loan applications a minute, speed is absolutely critical. Lime is consistently blazing fast because, again, it just fits a simple linear surrogate. But SHAP's quest for perfect mathematical exactness, well, that comes at a massive computational cost. Think about it for a second. Lime just throws some random points around an applicant and draws a line. We're talking milliseconds. It is totally amazing for quick prototyping. But SHAP, because it insists on being perfectly fair, has to test what happens when it includes and excludes every single feature in every possible combination. To get those exact Shapley values, you literally have to evaluate 2 to the power of F combinations. That is an exponential complexity that can take hours for production-scale models. Imagine your loan model has 100 features. Doing the exact SHAP math for just one single applicant requires computing more combinations than there are atoms in the observable universe. Seriously, no way. If you're using kernel SHAP, which is the standard model-agnostic version of SHAP, it relies on heavy sampling to approximate all this, and it's notoriously slow and incredibly computationally expensive.
However, don't panic just yet. If you are using tree-based models like XGBoost, we actually don't have to suffer through that exponential wait. And this is a massive deal because gradient-boosted trees are pretty much the absolute dominant algorithm used for tabular data, exactly like our loan application.
This is where TreeShap comes to the rescue. It brilliantly illustrates how we can essentially exploit the structure of the decision tree itself. It reduces all that crazy math down to polynomial time, which means predictable, manageable calculation times. It actually makes SHAP fast enough for real-time production inference. Instead of calculating every single combination blindly, TreeShap smartly traces the paths down the decision tree, allowing it to calculate exact Shapley values incredibly fast. Tools like FastTreeShap version 2 have optimized this even further, running like 2.5 times faster than the original. So suddenly, that huge speed advantage Lime had practically disappears if you're working with tree models.
All right, let's wrap this up. The conclusion: making the right choice. So we've walked through the trade-offs when it comes to both scope and speed. And honestly, understanding exactly when to deploy which tool is really the hallmark of a top-tier data team. Breaking it down, it's pretty straightforward. You want to use Lime for rapid real-time debugging, especially on neural nets, but you absolutely want to rely on SHAP for exact, consistent, global analysis on your tree models. If you need a fast local explanation on a massive deep learning model that's serving real-time traffic, Lime is going to be your best bet, because kernel SHAP would just bog everything down. But for your XGBoost or random forest models, TreeShap gives you both the speed you need and that exact global consistency that regulators are going to demand. Operational realities really force us to admit something important here. Neither method is entirely flawless. Without the proper context, either of these tools can absolutely be misused. People often fall into this trap where they assume that just because they have a fancy SHAP plot, their model is definitely acting rationally. But remember, these tools explain the correlations the model found. They do not prove absolute causality. If your model learns some spurious, completely silly correlation, SHAP isn't going to fix it. It'll simply faithfully report .silly logic right back to you. So, what are our final takeaways? Ultimately, Lime is like a great flashlight for taking quick peeks around the room. But SHAP? SHAP provides the consistent, golden illumination that's required by regulators to truly, deeply understand the black box. When you're building out your AI pipeline today, standard practice is now to compute SHAP values on a sample of predictions and systematically store them for drift monitoring and, of course, compliance audits. As these AI models continue to grow more and more complex every single day, I want to leave you with this one thought. When your next loan application is denied by an algorithm, do you think the law will prioritize a fast explanation or a mathematically flawless one? It is a question that every single organization deploying AI has to answer right now. Thanks so much for joining me on this explainer, and I really hope this helped clear up the heavy-hitting matchup between SHAP and Lime. Catch you next time.